Swayam Prabha. Digital India. Educated India.
Hi and hello everyone. What we have been seeing so far are the analysis of closed Jackson network, in which we first defined this what is a closed Jackson network or Gordon Naval network. We gave the solution as a product form solution even in this case, and the main complexity while computing the joint distribution arises in the computation of the normalization constant, which was g of n, and to compute the normalization constant in an efficient manner, we gave an algorithm which was called as Buzan's algorithm or convolution algorithm, because the terms, as you can recall, that the terms involving in the recursive computation are much like the convolution function. So, that is why this is also called as convolution algorithm. So, all these processes so far whatever we have used, right, so which require computation of this g of n, which is the normalization constant. Now, from the normalization constant we get the joint probability distribution, and once we have the joint probability distribution, we can then obtain marginal distributions and the expected value measures. Okay. So, what we are going to see next is an algorithm which can be employed if you are interested only in the mean value quantities or the expected value measures rather than the joint distributions and marginal distributions, right. So, this is a method which is called as this procedure is called mean value analysis, and the mean value analysis algorithm or MEA algorithm is an approach for calculation of expected value measures directly without involving or computing the normalization constant in case of this convolution algorithm, or directly in a naive computation way if you want to compute the joint probability distribution and hence marginal distributions. So, what this algorithm will give us is the expected value measures, which are mean number in any particular node and the mean sojourn time in any particular node is what we are going to compute directly. Okay. So, that is what is called as the mean value analysis, which is an approach for calculating the expected value measures directly, which is the mean number, mean sojourn time. In fact, marginal distributions can also be computed, which we can look at it in a simpler settings, but we are not going to look at it. But it is possible that marginal distributions can also be obtained using this algorithm. Okay. And this is now we are not computing this normalization constant or state probability distributions in the generality, right. Objective is to compute directly the mean value measures. Okay. How it does is that it recursively computes by incrementing the number of customers until the desired number of customer is reached, which means that you start with 0 customer, assuming that 0 customer, you do certain computation, then with use that idea to get the quantities corresponding to 1 customer in the whole of network and 2 customer in the whole of network and so on. So, suppose if your 100 is your number, then you increment up to 100 in each step, up to 100 steps. So, then you will get at the 100th step you are going to get the required performance measures of the closed queuing network that is under consideration with that 100 customers in this case. Okay. So, but this is based on two principles, and that is, the first one is called either the mean value theorem or the arrival theorem, okay, which we have seen in such scenarios when you have finite source and things like that. We have already seen it, which is also relevant here. What is that? The queue length observed by an arriving customer is the same as the general time queue length in a closed Jackson network with one less customer. That one less customer is probably himself or herself, itself, so to say, right. So, that is it what? And in a network with n customer, the arrival point probabilities of finding the system in n would be the same as the arbitrary time probabilities of finding the system in small n when there are capital N minus 1 customers in the network, right. So, this is the what is called as the arrival theorem or the mean value theorem. Okay. Probably is more easy to remember and appropriate the word arrival theorem because it talks about the arrival and what it sees in the equilibrium, right. This is the first principle that we apply. The second principle that we apply is that Little's formula is applicable throughout the network. I mean, for the combined as a network, it's also this Little's formula is applicable, okay, and each node also it is applicable. That's what we assume. So, this is it's happened. So, but it's basically these are the two principles on which the algorithm is built upon. Okay. But this algorithm, one has to be careful, this algorithm is applicable only to systems where the service times at each node are exponentially distributed, and also at each node follows FCFS discipline. Of course, it can also be expanded to more general queuing disciplines, but you have to look at it a little bit more carefully. In certain cases, the exact thing will be applicable. For example, single server, when you have each node, even the LCFS discipline, will be applicable, and some other discipline, whether it's applicable or not, there has been, if you want more detail or deeper ones, then you have to look at that. But we are assuming for simplicity that FCFS disciplines for which this is applicable here. Okay. So, that is the mean value algorithm's background. Now, the two principles gives us as basically the steps of how to compute the quantities, which is mean number and mean sojourn time in a recursive form for each node. Okay. Now, let us look at the first principle, which says that which is talked about the arrival theorem, right. So, the queue length observed by an arriving customer, right, in an capital N customer node network would be the same as the queue length observed at an arbitrary time with n minus 1 customers in the whole of network, right. That is what is the case. Now, recall for MM1, the W, which is the sojourn time in that MM1 queue, is basically equal to 1 plus L by mu. So, that is what? So, this is basically 1 by mu plus L by mu, right. So, what is the sojourn time of an customer there? It is his service time plus the service time of the average number of customers in the system, right. That is, so if there are L is the average number of customers in the system, each one service time is 1 by mu. So, L times 1 by mu is basically the average time to serve the queue size that he observes, okay, and plus his own service time, which is 1 by mu. This is the expression, but you know the expressions for L and W in this particular case very easily. So, L is rho by 1 minus rho and W is 1 by mu times 1 over mu times 1 minus rho, right. That is what you are seeing. So, you can see that that satisfies this relationship, but one can argue, right, one can argue also like how and what is the meaning of that relationship is basically you can think of this as 1 by mu plus L times 1 by mu, right. And here, because in MM1 AN equal to PN, so it is basically arriving customer or arbitrary time, both are one and the same, right. But here there is a difference, right. So, that is what you need to keep that in mind. And even if this is for MMC, in this case no adjustment is needed, as L is based on with the fact that AN equal to PN, right, is what is happening in MMC model also. So, MMC also this does not require any adjustment. But the equivalent condition in our case of this closed network, now we are assuming, remember that we are not taking the general case, we are taking the case where Ci equal to 1 here, single server node. So, with single server at each node, for the equivalence of this in our closed queuing network is basically this expression, because this is Li, right, because if you compute from the arbitrary time distribution with n minus 1 customer in the node, that is what an arriving customer would observe, right. So, that is why Wi, that is the waiting time of a network with n customer, you are looking at in the ith node here, right, with an n customer in the network would be equal to 1 plus the Li of a network with n minus 1 customer, right. So, the exact same relationship, but now this one will be with n customer, this will be with the n minus 1 customer, because of the fact that this is what you are observing, because Li you will compute using this, and that will be same as the Wi that you will compute using this n with n, right, that is what you are having here. So, this is the mean waiting time at node I for a network with n customer, and this mu I is the mean service rate for the single, how come this becomes single server at node I, and Li of n minus 1 is the mean number at node Y in a network with n minus 1 customers, as we have seen. So, the first principle, which is the arrival theorem, gives us this relationship for the closed queuing network. Okay. This is quite easy, but the second principle is what we are assuming that Littl's law is applicable throughout the network. That means that Li of n would be equal to lambda I of n times Wi of n is what we are taking it, right. Now, so if somehow if we can find lambda I of n, which is the throughput at node I, or the arrival rate at node I with a network with capital N customer, then we have a method of calculating Li and Wi starting with an empty network and building up to a network with capital N customers, because Li of 0 is 0, right. Li of 0 is 0 when there is 0 customer. So, there is no number of customers is 0, and when there is 1 customer, the waiting time is his service time only, right. So, you have this. Now, once you have this, assuming that my lambda i's are there, right. Now, you can see that this relationship, this Wi n depends on Li n minus 1, right. So, now what I have started with Li of 0 is there, Wi of 1, of course, you are basically getting it from here, you can think. Now, once I have Wi of 1, from this relationship, then I will get Li of 1. Now, once I have Li of 1 here, then I can go to this and then I will get Wi of 2. Now, Wi of 2 if I have, I substitute it here again, then I will get Li of 2. So, you see here there is a way of computing Li and Wi successively until whatever the number of customers that n you want. Okay. So, these are basically the two steps that you involve, but then you need to know what is this throughput lambda I of n, right. If we know that, then we can do this. Okay. So, now how do we compute this lambda I of n, right? That is what is the main part in this result. Okay. Now, for which note that we want to compute this lambda I of n. So, for which we define di of n, this is the average delay per customer between successive visits to node I for a network with n customer. Okay. So, it is between what is the average time once it leaves this node I, what is the average delay to average time it takes to come back to this node again. Then per customer, that is right. So, then per customer arrival rate would be, as per the laws of conservation, it will be 1 over di of n. You have seen in Markov chain and elsewhere to the similar analysis, right. Now, since the network has n customer, so the arrival rate, right, lambda I n would be n over di of n, right. So, this is what you can do. So, if I have this di of n, then my lambda I of n is n over di of n, because this is the time it takes. So, per customer arrival rate to the node I is 1 over di of n, and since there are n customers, so this is n over di of n is what you will get as this lambda I of n. So, now then we have to get this di of n. Okay. So, how do we get this di of n? So, to get the di of n, we return to our traffic equation, which is mu I rho I, which is equal to summation mu j rho j times r j I, and we set this mu I rho I, because we set rho I as the relative utilization, and this, so mu I rho I would be nu I. So, now this is relative throughput or relative arrival rate. So, where so that means that then the equation is basically this, if I substitute mu I rho I equal to this V I. Okay. Now, since we know that this set of equations is a linearly independent system, so you can set one of these nu I equal to 1, say let us take nu L to be 1 and solve for others. We know that this nu I are the relative throughput through node I, which is basically nu I is lambda I by lambda L is what is this nu I. Now, once we have this nu I, then we can write this dl of n as the weighted average of the weights that happens in all the nodes before it comes back to. So, this is weighted by this nu I, which is the relative throughput. Okay. So, basically what we have, this is the expression that you need to keep that in mind. So, this is the weighted average of the average delays at each node weighted by the relative throughputs, which is basically this nu I here. Okay. Or equivalently, you can think of this as weighted by the expected number of visits to each node prior to returning to this node, normalized node, which is L here. L is the normalized node that we are taking, because you can imagine this nu I can also be interpreted as the expected number of visits to node I after leaving node L prior to returning to node L. So, this visit count quantities we have not defined for this network, but that is the interpretation that we can give for this. Say for example, if we have a 2 node network with nu 1 equal to 1, right, and nu 2 equal to 2, then since the arrival rate at 2 is twice that of node 1, that is what we call relative throughputs, relative arrival rates. Nu 1 equal to 1, nu 2 equal to 2 means whatever be the arrival rate is node 1, in arrival rate at node 2 is twice of that. So, the expected number of visits to node 2 after leaving node 1 and prior to returning to node 1 must also be 2. That is why, that is when that is how it will be satisfying, right. So, once we have this nu I, so that means that dl of n I can compute, then I can compute this quantities lambda I of n. So, the lambda I of n we can compute it. This is the background behind this algorithm. So, now we can write it down the algorithm. Many a time like the algorithm is directly written, but you can give little bit of understanding at what is the step that you can involve. So, this is called MVA algorithm. The objective is you are finding the expected value measure in a k node single server per node network with routing probability matrix as usual R. What we have the traffic equations nu I, which we have written down now for the relative throughput, and you set one of these nu I, say nu L equal to 1 and solve for the remaining nu I's from this set of equations. You initialize this to this, Li of 0 is 0, right. Now, for n is equal to 1 to n, you repeat these steps A, B, C, D, okay. This is the repeat steps. So, the first one is Li of 0 you have initiated. Now, for n is equal to 1, then you will compute Wi1, which is 1 by mu I for each of these 1 to k nodes, right. W1 of 1, W2 of 1, W3 of 1 and so on you will compute, that will be equally 1 by mu 1 or 1 by mu 2, 1 by mu 3 and so on. Once we have that, then you compute the lambda L of n, right, based upon this, that is for the normalized node that you are picking it up, right. So, assuming that nu L equal to 1, now corresponding to that L, you compute lambda L of n, which is n over this quantity, right, which is what we have just seen, that this is what is your d L of n, small n, and this is n is the now in this particular step for n is equal to 1, n is the number of customers in the whole of network. So, this is the arrival rate of the normalized node that we are picking it up. Then we know that lambda I is basically nu I times, because nu I is basically lambda I by lambda L. So, lambda I is equal to lambda L times nu I. Now, once I get this lambda I n, then I can use the second principle that we have used. So, the first principle is used in A, the second principle is used actually in D. To lead to D, we are computing B and C, the steps. Okay. So, lambda I n, W I n. So, lambda I n once I compute, then I will get this W I n from step A, I plug it in, I will get lambda I n. This is for n is equal to 1. Now, that means that you are computing for one customer. Now, n is equal to 2, which means that you are computing for n is equal to 2 customer with the corresponding Win and Lin, because that is what you know. So, this is how you iterate until up to capital N, which is the objective that you wanted to compute with capital of n customers in the network. So, this is what is the MVA algorithm in a single server node network. That is what we are seeing it here. Now, we can take up the previous example, but with a slight modification, because there we have assumed 2 machines. If you recall the examples that we have considered earlier, which is basically this diagram if you can recall. So, now we have assumed 2 machines and then there is local repair, specialist repair. Now, we will assume this one machine here, that is the change that we will make, so that this will become a single server at each node network. Okay. But the values that we will pick it up is again the same value, right. So, which will have this G2, and if you want to compute, so this is all you will get exactly same. So, this is what you will get here. Okay. Now, with that understanding that we will take up the same example, 2 machine 3 node network, but now with 1 machine. So, it becomes a 1 machine 3 node network. So, the traffic equation then is nu is equal to nu times this R is this matrix for the values that we have assumed. We will choose nu 2 equal to 1. When we solve for row also we pick that row 2 equal to 1 and we obtain the other one. So, in a similar way nu 2 equal to 1 we pick it up, which means L is 2 here in this particular case. That is what we are picking it as one of the nodes as normalizing node. So, that is L what we are denoting it. So, nu 1 is 4 by 3, nu 3 is 2 by 3. So, which means this is relative throughput means if nu 2, for nu 2 if arrival is happening at the rate 1, then for nu 1 it is 4 by 3 times of the corresponding arrival rate in nu 2, right. That is what we are calling it as 4 by 3 and 2 by 3 of this measure. Okay. So, now for I is equal to 1 to 3 and n is equal to n equal to 1, now here there is only one customer, because there is only one machine. So, there is only one customer. So, now capital N is also equal to 1. So, we need to apply this algorithm for only one step. Okay. So, from the first step, of course, we have the initialization condition is L1 of 0 is 0, right. So, the first step is W with bracket 1, right, W1 of 1, W2 of 1, W3 of 1, because there is 3 nodes. So, L1 of 0 and the first node it is lambda is the rate. So, lambda was 2. So, W1 of 1 is 1 by 2, W2 of 1 is basically 1 by mu 2, which is 1. W3 of 1 is basically 1 by mu 3 because this is L1 of 0, L2 of 0, L3 of 0, all of them are zeros, right. So, this is 1 by 3 because mu 3 is 0. Now, lambda 2 of 1 we can compute once we have these W's. So, and we have this news from here, nu i's and W i's you have. So, you can compute now lambda 2 of 1 as 9 by 17 and hence lambda 1 of 1 is 12 by 17 and lambda 3 of 1 is 6 by 17. Now, once we have these two, then I can now compute L1 of 1 which is lambda 1 of 1 W1 of 1 which is 6 by 17. So, L2 of 1 which is lambda 2 of 1 and W2 of 1. So, lambda 2 of 1 is this and W2 of 1 is this. So, that will give me 9 by 17. L3 of 1 in a similar way is 2 by 17. Now, since in this particular case n is equal to 1, we are done. Okay. That is what you have in this scenario. Okay. So, this is so you can now obtain the Wi's and mu Li's in each node in this network, but single server case. So, now recall you can verify whether this result is true by a verification process, right, because you know already the joint distribution, right. So, the solution of the traffic equation was rho 1. So, we assumed that rho 2 equal to 1. So, rho 1 was 2 by 3, rho 3 was 2 by 9. Again, this is relative to this rho 2, right. If rho 2 is 1, then rho 1 is 2/3 of rho 2 and rho 3 is 2/9 of that. That is what we have, right. So, then P of n1, n2, n3 was 1 over g of 1, 2 by 3 to the power n1 and 2 by 10 to the power n3 was the joint distribution. So, that implies, right. So, what are the possible number of states? It is 3 node single customer. So, the customer could be either in node 1 or node 2 or node 3. So, the possible states are 1 0 0, 0 1 0 and 0 0 1. These are the only 3 possible states, and for each of this you can compute these quantities. So, for 1 0 0 this will be simply 2 by 3 divided by g of 1, and for the 0 1 0 it will be 1 over g of 1, and for the other third one which is 0 0 1 it is 2 by 9 divided by g of 1 is what you will get as the joint distribution. Then these 3 must sum to 1. If you compute g1, then g1 will turn out to be 17 by 9. Now, once we have this 17 by 9, then you know that 2 by 3 by 17 by 9 will give you this, right, and this is 1 over g of 1. So, it is basically 9 by 7 and this is 2 by 17, and which from here we can now compute this L1, L2, L3, right. What is L1, L2, L3? See, in this particular case it is just 1. So, it is basically 1 with this probability, 0 with this probability, 0 with this probability to get at the number in system number in node 1, right, which will turn out to be simply 6 by 17. And similarly for L2 9 by 17, and the probability itself is turning out to be that because there is only one customer in the system and there is only this many states. So, this is corresponding to that probability. So, that is the average number also, right. Now, once I have this, now lambda once I can lambda 1, lambda 2, lambda 3 I can have already computed this, right. Now, I can use Little's law again to get this W which is L by lambda, right. So, I can get this W's which is 1 by 2, 1 and 1 by 3 from this joint distribution. Now, you see from the joint distribution from here I can obtain these L's. It is simple here, it is not a complex here, but in a more complex situation obtaining this is not very easy because obtaining this G of this is not easy. But if you wanted to compute the joint distribution at any cost, you have no choice, you have to compute it, right. But if you are interested only in the mean values, then one can directly apply the MB algorithm, which might be very simple to apply because you are directly computing the mean values directly here, right. This is a verification that you can do, you can look at it. Okay. Now, this algorithm can also be used to get the marginal distributions, but we are not looking at that part. But what we will just state it along similar line is that what is the MV algorithm in the multi-server case, because this is the more general one. that you can take. Now, to do that we need to define two other notations. Of course, this alpha ij you already know, but we are just giving this notation, but there is another quantity which is pi of j comma n, which is the marginal probability of j at node I in an n customer system. So, the total number of customers in the network is small n, and at node I the number of customers is j. What is the probability? This is the marginal probability that we are denoting. Okay. And this alpha ij is basically in the ith node. What is this quantity j, which is j and c of I, which you will know that okay, this is connected with this MMC model, like for the recursive pk plus 1 and pk, if you connect it, you will have lambda by some quantity times mu. That some quantity is what this either j or c, depending upon whether j is less than c or greater than c, right. So, this is that quantity, this is a notation. Okay. These are the two things that we got. Now, here what objective is again this, but now CI servers at node I with wrote this. Again you have this traffic equation remain the same, that does not change anything. So, setting one of this which say nu L equal to 1, you have to solve it. Now, your initialization condition is not just this, the Li of 0 is 0, you had it for single server also. But now you have additionally these conditions as part of the initialization process, which is pi of 0 0 equal to 1, pi of j comma 0 for j not equal to 0, right. We are seeing this must be equal to 0 because total number of customers 0 and you find j customer in the node, it has to be 0, right. So, this is 0. When there is 0, what finding probability 0 in system is 1, that is what you are getting it here. Okay. These are the initial conditions or the initial starting condition or stat. Now, again you will repeat here, but now the change that you will make is basically in this step and in the last step, because that is what naturally will happen. Okay. So, here you do not change, but this additional step that we will come back to that. Okay. So, in this step what is the change, because now there is not one customer or one server here, it is Ci number of servers, right. So, this is essentially derived based upon that, but if you want to look at more you can refer to the text. It is just a simple argument that how you arrive at this expression. Okay. So, that is basically depends on, let me quickly see. So, that is basically depends on, suppose if you have Ci servers at node I, and then if you have j minus c I plus 1 customer with the corresponding probabilities given by this, then this waiting time. So, that is the number in the system it will become. The Li, that L would be replaced by that quantity, and with that simple little algebra then you will arrive at this expression. But now what we are seeing here is that this is actually a marginal distribution, right. But even in this multi-server case, in single server case, we did not require this marginal distribution in the computation of this WIs and okay. But in the case of multi-server system, okay, this is required. So, up to Cj minus 2 or Ci minus 2 for at each node, up to that you need these quantities in order to compute this W. It is not just on Li of n minus 1, you also need the marginal distribution, some marginal distribution value. So, that is what one would compute here in a recursive manner again, that will be involved in this. So, that is the main step here. So, the main step that requires modification is in the computation of Wi when you are going for multi-server case, and that would lead to this expression here that we have written down. Okay. So, this is what is the, once you have done, then the remaining steps of the original ABCD steps are remain the same, but now since this is required with for example, in this when you are to compute with n customer in the network, you need this Pj with n minus 1. So, you have to compute, right. So, you start with 0. Now, when you do this 1, then Pj 1s are needed to compute in Pj 2s. So, the Wi 2s, right. So, this is basically the relationship lambda I by either j times mu I or c times mu I, depending upon where this the j is, right. So, that is what is this relationship. This is the usual recurrence relationship in an MMC model between the steady state probabilities of being in state k and state k plus 1. There is nothing here beyond that, okay, it comes from there. Okay. But one can easily show that also this is true in single server case and multi server case and so on. But whatever it is, this is the algorithm. Now, with this algorithm, you can now take it up the original problem, that example that we have considered, which is basically 2 machine and 3 node problem, right, closed network example. Now, you can apply this one to get the mean number of Wi's and Li's from this. So, that is what it happened. So, you can again by computing joint distribution also we have already computed, right. Now, you can compute, you can do the verification of the result also from the joint distribution. Joint distribution we already computed, you do not need to compute it again, right. But from there marginal distributions and then the corresponding Li's and Wi's you can compute, and you can match with this MVA algorithm, whatever value that you are given, you can just do. Okay. So, this is all about MVA that we are going to see. We are not going to go beyond this level, but we may end with what can be said about these 3 processes, the brute force or naive computation of G directly and the convolution algorithm and the MVA algorithm. As you have seen, all 3 methods are easy for small problems, right. For smaller k, smaller n, it is always possible that any of these you use, you do not have problem. At least for our pen and paper calculation that we do, all 3 methods are actually one and the same. So, you really did not feel the need of these 2 things, right. One can do directly a naive computation with 2 customer, 3 customer, 3 node, 2 node, 4 node, like you can always do this computation very easily, it is not a problem at all. But basically like but in reality that is not the case, right. So, you have to implement it with a large number of nodes or large number of customers or both, that is what we call simply as larger network. In that case, this Bhujan's and MVA algorithm or the convolution algorithm and MVA algorithm are computationally far superior over the naive computation with respect to efficiency, which is in terms of storage and speed, and the stability for larger problems, numerical errors and all other stuff you can put together. For larger problems, these are computationally far superior. Okay. But between these 2, if you want to compare, right, what would be the best or better? Now, for a single server at all node network, like the case that we first considered within this MVA, MVA is superior if we want only the mean waiting times and mean system size at each node. We do not want the state distributions, right. If we want only the mean, then this is superior. But if you want there either the joint marginal distributions or even if you want only the mean, but you have multi-server nodes, right, or if you want marginal probability distributions, it is not clear how much is better, if it is really better. Maybe in some situations MVA might be better, in some other situation convolution procedure might be better. That depends on the situation and what kind of things that you want and so on. Okay. So, and hence both of these are essential in order to have a complete understanding of the closed queuing network or the garden naval network that we have seen in this case. So, naive or brute force approach is applicable easy in case of very small networks, but larger networks, since it is not clear which one will do better in which situation, because you can always find a case where this is better than this has performed better than the other one in the kind of network that one has analyzed. So, it is not clear, since it is not clear that it is which one is better. So, it is always better that you know about both, but a crude way is that if you are interested only in mean and mean values, you can directly go for mean value algorithm rather than computing the convolution process. Convolution process gives you that G of n, right, but product form is there, G of n only you need it. So, that one alone you can compute through convolution process. Okay. But if you only want mean, directly go for MVA algorithm. That is what normally one would do. Okay. So, we will end our discussion on closed queuing network, this type of closed queuing network now, like we will take up a bit more on these ideas in the following lectures. Okay, thank you, bye.